Hello, and a very warm welcome to the fourth Mod Alliance webinar. My name is Teresa Fonseca, and um, on behalf of DiverSea Project, I'll be your host today. And I'm from the Portuguese environmental NGO League for the Protection of Nature and responsible within DiverSea for the communications. We are delighted to have you here with us for this session. Please note that today's webinar will be recorded. If you have any issues with being recorded, we recommend that you switch off your cameras during the event. Thank you for your understanding. So to set the stage, we'll start with a short video that gives you an introduction to the Mod Alliance and the work we do together. I'm going to share my... Oops, sorry. So, the Mod Alliance is a collaborative platform comprising the communication efforts of three of Horizons Europe's sister projects, Marco Polo, Obama Next, and DiverSea. The projects in Mod Alliance are funded under the same core topic, with a shared focus on observing and mapping biodiversity in ecosystems, with a particular focus on coastal and marine ecosystems. This alliance aims to unite our efforts and amplify the impact of each project. We want to share progress, promote collaboration, advocate for the preservation of coastal marine environments. The three projects complement each other and work towards common goal through joint initiatives such as this webinar series and a dedicated communication web pages driving positive change for better waters, better oceans, and a better planet. This is the fourth webinar of the series. Today's webinar is hosted by DiverSea and it's supported by Marco Polo and Obama Next. Here today, represented by Mathilde and Miguel. The next webinar will be moderated by Marco Polo in November. So in this webinar entitled Exploring Coastal Habitats Through Marine Robotics, Benefits and Challenge, our expert speakers will offer insights into the potential and limitations of marine robotics in real-world research. They will explore how autonomous systems may help us better understand and manage complex coastal environments. We are very fortunate to have the excellent presenters with us today. Lucrezia Bernacchi, who works at the Faculty of Engineering of the University of Porto in the Underwater Systems and Technology Laboratory, LSTS. She conducts research on marine robotics and contributes to software development. Lucrezia holds a bachelor's degree in mechanical engineering from the University of Florence and a master's degree in robotics and automation engineering from the University of Pisa. Her work has consistently focused on underwater robotics, spanning acoustic communications, mission planning, and operations. Miguel Carvalho is a researcher, software developer at INEGI, with master's degrees in both robotics and intelligence systems and in computer and telematics engineering. He has wide-ranging interests in automation, machine learning, and cybersecurity, and is currently focused on his passion for marine robotics with the Underwater Systems and Technology Laboratory. So, just before we begin, a quick reminder, there will be time for questions at the end of the presentation. If you'd like to ask a question or share a comment during the session, please write it in the chat. You're also welcome to briefly introduce yourself in the chat so we can know who's with us today. So now over to Lucrezia and Miguel. The floor is yours.
Okay, thank you so much. Can you hear me? See, okay, so thank you, Teresa, for the introduction and for organizing this series of webinar. And so, hello, everyone. Thank you for attending this presentation. And so, as already know, I am Lucrezia. So nice to meet you. Let me just share the presentation. Can you see the presentation? Okay, so let's start with this webinar. So this is an outline of what we will speak about. So a quick introduction about us, who we are, what we do. Then we move on the main topics of the presentation. So marine robots, why are we using them, how they work, and which kind of information they are able to provide us. And then I will leave the floor to my colleague Miguel, and we will see all this technology in a real scenario in the context of DiverSea project. Something about us. The LSTS, Underwater System and Technology Laboratory, is a research laboratory born in the University of Porto and now part of INEGI. In LSTS, we are specialized in the design, construction, and operation of unmanned vehicles. Unmanned vehicles that can be aerial vehicles, surface vehicle, and also underwater vehicles. So something that is our key point in our technologies and our development is working with the network vehicle system, meaning that this is part of our assets. So as you can see, we have different kinds of vehicles, surface, aerial, underwater. Some are owned by us, other were bought from external vendors. But even if they are different, they are all powered by the LSTS software toolchain, meaning that we can consider this system as the same system. So each of them is powered by the same software. They can talk with themselves, so they speak the same language, and they are operated with the same interfaces and software. If you are more interested in the LSTS software toolchain, here you can find the link to our webpage, and you can find more information, or you can send an email to me or Miguel. And so that was just an overview about what we do. And so now let's start with the marine robots topic. So why are we going to use marine robots? What's our goal? So in this context, the goal is to acquire data. What we want is a wide variety of data, okay, in order to be able to monitor, to understand what is going on, and to predict, to check the status of our ocean, seas, coastal environment, and so on. In order to get this data, we can use different kinds of technologies. Each of them has a specific positive and negative aspects, of course. Nothing is perfect, but for example, if we want to obtain some data using satellite, then we can have data that cover a wide spatial area, like all this image that we can see here. But if we are interested in knowing a specific value, for example, of temperature in some specific pixel of this image, then the satellite is not the best solution. So we can use other kind of technologies. We can use the research vessel or buoys. In the first case, we can deploy our instruments from the vessel and obtain specific data in specific location. Of course, we have to consider also the operational cost in doing this. Also, we need to consider that then we have point-based measurements and not covering a large space. So in this situation, autonomous vehicle can help us in the sense that they can take data from in situ location, okay, but since they are able to move, they can increase the spatial coverage, and plus they are cost effective compared to the operational cost of research vessels, and they are electric powered, so lower environmental impact, and they are silent, and since they can navigate autonomously, they can also have a sort of intelligence in order to change their behavior based on the information that they are collecting. And last but not least, they are agile and small, which is something that we should not underestimate when we are considering coastal environment, because the free space of navigation is different compared to open water. In this case, we can have some specific constraints. For example, we can find rocks, then there are incinerations. In some area, we have very, very shallow water, and the depth in the different areas can change because of the tides. Some negative aspect of this technology, just some of them, like for example, they cannot operate forever, so they have a limited endurance. Then they require experienced operator for now to operate them. And then since they are small, we cannot equip them with very small and heavy payload. Okay, so nowadays we have a lot of different kind of robots, some of them with cables, some that can travel completely, navigate completely autonomously, surface vehicles, underwater vehicles, wave-propelled vehicle, electric vehicles, plenty of vehicles we have. And what we are going to see in this slide is we are taking as example the light autonomous underwater vehicle, and we want to point out the main component of these autonomous electric powered underwater vehicles. So starting from the first point, the power supply, we have batteries that are power everything that is inside the vehicle. These batteries can take up a very large portion of the interior part of the vehicle. So the more battery we have, the more endurance we have, but we need to be careful because then we have less space for the navigation sensors and for the sensor that we want to acquire actually the data that are useful for us. And so we need to trade off these two things. Then propulsion system. We have a propeller on the back responsible for the backward and forward propulsion, and the fins in order to let the vehicle be able to turn. Regarding the communication, in the antenna we can find everything that allow us to communicate with the vehicle through Wi-Fi, GSM communication, and satellite communication. Then to communicate with the vehicle underwater, we have the acoustic modem. You can see it on the bottom of the vehicle. And regarding the navigation, here we can see the inertial navigation system and the Doppler velocity log. We are going to speak about this in a bit. Was just to point out these two kind of sensor. And then we have the CPU, one or more, that can be just considered as the brain of the vehicle, is responsible to everything, to manage the communication, the navigation control, plan execution, sensor, and so on. Okay, so let's pretend we are in an operation. So we deploy the vehicle from the boat or onshore if we can. The vehicle is on the surface, the antenna is outside the water, so everything is perfect. We have communication, Wi-Fi, GSM, Iridium, so satellite communication, and we also have the GPS signal. So for the navigation, we don't have any problem. The vehicle knows where it is. Let's pretend that he knows where it has to go, so it can control itself autonomously to reach the specific point. Okay, when the vehicle is underwater, the situation is different because the radio waves are attenuated by the water medium. So the vehicle, any waves reach the vehicles. The vehicles cannot communicate with us, so we don't have communication. We don't have the GPS signal, so the navigation task is complex underwater. So regarding the communication, what we can do is to deploy acoustic modems, if we can, from shore or from the boat, and we can talk with the vehicle with the acoustic modems, because the acoustic waves can travel long distance underwater, in contrast with the radio waves, and of course the bandwidth is not that big, so we cannot exchange a big amount of data, but we can communicate. Okay. Regarding the navigation, underwater navigation is a very complex task, and there are different methods. Some are based on the acoustic positioning, and what we are going to see right now is just the depth reckoning technique. So the logic of this the depth reckoning is that the vehicle estimate its position, so knows where it is, just using the information of the sensor that it has on board. So let's pretend he knew where it started, the mission, because in that moment he had the GPS signal. He knew that he moved 4 or 5 seconds at a specific speed in a specific direction. And thanks to this information, he's able to understand where it is now. Okay, in order to do this, he needs information about the movement, okay, and the acceleration and the direction. For this, we have the inertial navigation system inside the vehicle. We can have also different kind of sensor, but the inertial navigation system contains the main sensor accelerometer for the acceleration, linear acceleration, the gyroscope for the angular velocity, and also contain the hardware and software part to compute the math that is behind that reckoning. Okay. The problem here is that the more the vehicle stays underwater, the more error we have in the estimated position. So in order to fix this error, we can use the GPS fixes. So we let the vehicle resurface, acquire the GPS, and then dive again underwater and complete the mission. Or we can also use the sensor that I was showing a few slides ago, so the Doppler velocity logger, which is an acoustic sensor that is able to give us the speed of the vehicle because it is using the Doppler effect, so computing the shift difference, the shift of frequency of the transmitted wave and the received one is able to understand the speed. And this is useful to correct and improve the estimate that the reckoning is doing. So why this digression in underwater navigation? First, because for someone that is not working in the underwater context, is not something can be something that is not trivial to understand all these problems that we can have underwater. And then because we are interested in collecting data, but collecting data without knowing where this data actually were taken, then it's not that useful. So it's important to correlate the data with the location of actually this data, because otherwise at the end of the mission we have plenty of data. For example, temperature of a specific area and the coast of Portugal, but then we don't know exactly which temperature belongs to which place. At the end of the mission, the vehicle is on the surface and we can transmit all the data with the related navigation data. Okay, so, let's see some of the sensors that this vehicle can have. Okay, so we must see this vehicle as a case, and we can attach to this vehicle the sensor that we need to collect our information. Here are listed some sensors that we are using. So starting from the easiest one, the CTD sensor is able to give us information about conductivity, temperature, and depth of the operational area in which the vehicle is navigating. Chlorophyll sensor for the chlorophyll concentration. And then we have here an acoustic sensor, Suscan sonar, cameras, and a eDNA prototype sensor, which is a prototype developed by INEGI in collaboration with Porto in the context of DiverSea. So we are going to see these three sensors quickly, but more in detail in the next few slides. So starting with the video cameras, what we want to do with the video camera is very intuitive. We want to see what there is underwater, what there is on the seabed, and the camera is on the back of the vehicle pointing down. So let's pretend that we want to know what there is underwater on this red operational area. So we create a mission that the vehicle can perform autonomously. We create this transit that you can see here in black. And then while the vehicle is navigating and performing the mission, is acquiring images, okay, of the sea bottom. So at the end of the mission, we have all these images in the folder, okay, and we can analyze these images, but what we want is a big high resolution images, which is way more easy to analyze compared to multiple single high resolution image. And this is possible thanks to the navigation data that we have, so position and orientation of the vehicle during the mission. And with this information, we can start assembling the underwater orthomosaics, which is a big picture, high resolution one, that can be used to analyze the specific things that we have underwater. So we can check some specific species. We can analyze the coverage of the specific species. How can they change in time if we are going to the same area multiple times? And this is what we are asking from the camera, but it's the same thing that we are asking to the side scan sonar, which is a different sensor, completely different sensor, is an acoustic sensor, not an optical one. But the goal is pretty much the same. So we want to know what there is underwater, okay? And the side scan sonar work with the acoustic waves. So we have two side scan sonar, one in each side of the vehicle. The side scan sonar is transmitting waves, and then the waves reflect to the bottom and come back to the side scan sonar. So the side scan sonar, thanks to the energy of the reflected echo and the time of flight of the waves, is able to translate these two information in a color information, because the different material can reflect the waves in a different way. So, for example, in this image we see black where there is no echo, or gray where there is the sand. Then here there is a stone with a different color, and so while the vehicle is performing the same black mission, is assembling this line while it's moving, and at the end what we have is what we can obtain with the same procedure of the camera is a big picture of what there is on the sea bottom, which is not that nice, this one, but it's just an example. And okay, as a last sensor, we have the eDNA passive sample prototype developed by INEGI and Porto for DiverSea. And the idea behind the sensor is to equip the vehicle with this sensor. And then while the vehicle is moving underwater, is collecting underwater in the filters that you can see here. And then when the vehicle finishes the mission, we can retrieve the filters and analyze the filters on shore. Okay, that's why passive sample. It's still a prototype. As you can see here, you can insert. You first put the filter inside these two green and red structure. Then you can insert the filter inside the stabilizing cylinder. Then the vehicle runs the mission. Then you can take it off and analyze the filter. We tested this prototype in a real context in an airport in Portugal, and we are still waiting for the analysis of the DNA, and we are planning to create a more light design and small design for the vehicle, but as I was saying, this is a prototype, and we would like to know if this approach is actually worth it. And okay, so I would like to conclude my part, just speaking a few slides about the mission planning. So what we saw in the previous slide was a simple operational area, just a square, the orange one, and a simple mission. And the idea was to create the mission in order to, while the vehicle is performing the mission, with the footprint of the sensor, is able to cover all the area of interest. So in order to do this, we need to take into account a few things. For example, that the footprint of the sensor change based on the altitude in which for which we want to perform the missions. That then we want a specific overlap that can change, but a specific percentage of overlap between the two footprints, since we don't want any holes in the orthomosaics. And these two information provide us the distance between the transit. And then another thing that we need to take into account is that we want to minimize the turns, because every time that the vehicle is turning, for example, if we are using an acoustic sensor, we can have a degradation of the image. Okay, but what if we have a more complex area, so not the square one? That is something that is very common actually when we operate in a real context in a coastal environment. And maybe we have also obstacle inside this area. So we don't know if the best path is this one or this one. We want to find the best path in order to cover with the footprint of the sensor all the area of interest. This is the well-known problem, which is called the coverage path planning problem. the literature is plenty of different solutions and methods to address this problem. In the context of DiverSea, we are trying to developing our strategy for this problem, and we want to do it in a bigger picture, meaning that we want to have an input, an orthomosaic, so an image which is georeferenced, previously acquired with the survey with the drone, and then with this image we want to obtain in output an optimal mission for the LOV in order to cover all the area of interest. So the main step of this approach are first detect in an autonomous way the obstacles that you can see in red. In this case, it's just the coast and too much shallow water. And so we want to detect them autonomously and then in an automatic way. And then the free space of navigation is divided in a grid based on different aspects. For example, the footprint of the sensor, the overlap that we want, maybe the orientation that we want for our mission based on currents or other things. So we want to consider different aspects in this the grid cell decomposition. And then we solve an optimization problem connecting the center of this grid in order to obtain the optimal path. So we test this approach, which is still under developing in different situations, also with a fake obstacle in the operational area. And yeah, that's it. That was just an overview to explain that mission planning cannot be, can also be not that trivial. And we are working on trying to use as much intelligence we can, trying to reduce the human effort in this kind of mission. And now I will leave the word to okay.
So thank you, Lucrezia. Right now we have been talking about how our vehicles, our fleet of vehicles and technology work in theory, but let's now see how these systems are actually used in a real case study scenario. So in particular, in the context of DiverSea. So DiverSea is a project which stands for Integrated Observation Mapping, Monitoring, Prediction for Functional Biodiversity in Coastal Seas, and is part of the Horizon Europe program. It's a 4-year of this project, and it's a project 14 different countries from all over Europe. This project, what's the main goal of this project? What is in fact DiverSea? So DiverSea intends to address the problems caused by the high exploitation of coastal ecosystems. We are all aware that because of this high exploitation, we can observe certain consequences, such as the decline in marine species evidence, diversity, and habitat degradation, for example. DiverSea wants to understand what is going on, how all this is linked to us, and our role in this decline, what we can do to avoid it. Specifically, we want to understand a direct link between exploitation activities and these consequences, which activities have a bigger impact or smaller impact on the consequences of this exploitation. And how will this be achieved? So by selecting multiple regions over Europe, we will map their physical, chemical, and biological systems, as well as their interaction and how they are interacted with. Afterwards, we will monitor these areas, or better yet, these ecosystems, closely over time to note changes on them. And finally, according to these changes that we note over this period of time, we want to predict and plan a response to those same changes. In the end, we intend to have a platform capable of informing users, given a set of changes to an ecosystem caused by this exploitation, for example, which actions should be taken to minimize the impact of these activities. As previously mentioned, we have 19 partners from 14 different countries distributed all over Europe, and they have been assigned to map and monitor specific zones across Europe, applying different methods to do it. For example, There are case studies which focus on, for example, autonomous vehicles, which is our case, snorkeling and scuba diving, remote sensing, public engagement. In our case, as I mentioned, we will focus on using our fleet of vehicles to gather data from the Atlantic coast of Portugal, in particular, the Luís Saldanha Marine Park. So this the park, the Luís Saldanha is a park of the Natura 2000 network and is located in the south of Lisbon. The park is considered to be an oasis of for marine life, and to protect it, protection zones have been established throughout its perimeter. There are areas where certain types of activities, such as fishing or diving, are allowed, and other areas where that is not allowed. This is an image of the park extension, and according to its perimeter, we have selected specific zones according to the different habitats, protection areas, hotspots for seagrass, for example, and other parameters. As you can see on that image, we have 4 red marked areas where we intend to gather that data and map the areas. So what do we actually want to do on these areas? We want to first evaluate and map the sea bottom habitat by collecting relevant data in these areas, creating a spatial evaluation of them, and then come back every year for missions in those same areas so that we can have a temporal evaluation of them. Once a spot is selected, in our case, we are now talking about Praia dos Coelhos, which is inserted in one of the areas, in order to have a wide coverage. In order to have a wide coverage map of the area of interest, we apply our multi-vehicle approach. And what is this? Different kinds of vehicles and technologies are used in order to have a complete coverage of the said area. So in the deeper regions, we will use underwater vehicles. For the regions closer to shore, we will use surface vehicles, or in our case, we reuse the underwater vehicles because we are able to operate them at the surface level. And for the intertidal areas, we will use drones. So for the intertidal areas, we will use UAVs, unmanned aerial vehicles.
Miguel, have you frozen?
Zones close to shore, UAVs, they use an autonomous and so that we can collect using the data, and for example, including cameras and LiDAR and the AUV equipped with the side scan sonar and camera, enable the creation of high-resolution images, as previously shown, mosaics of intertidal, shallow, and other water areas, providing essential material for species identification, habitat classification, and coverage assessment in different locations of this marine protected area. Again, we intend to periodically deploy, and we have been doing so for the last 2 years, deploy these robotic technologies in these same areas so that we can support temporal monitoring and provide valuable insights for conservation measures and potential future actions on these areas to increase its protection. In addition, the integration of this heterogeneous data from both air and the water domains can clearly demonstrate the potential of using multi-platform robotic systems to bridge this observation gap across coastal gradients. So with these coordinated missions, we can contribute to the ongoing research in automated image analysis as well and mapping techniques. And for example, for our intertidal region, the UAV we used in particular was the DJI Matrix 350 RTK, which is a high-precision drone, which supports joystick control and autonomous flight along predefined areas, providing real-time, highly accurate 2D and 3D geospatial data, which can then be used to generate point clouds and also mosaic images of the inspected areas, such as these ones we can see on the next slide. So here are the results of the AUV from some of the missions we did on Praia dos Coelhos over different periods of time. For both the shallow and deeper regions, however, use the AUV and ASV again because our AUVs are actually capable of operating at the surface. We decided to use the vehicles you see here, which are equipped with the DVL, the side scan sonar, the acoustic modem, camera, for both of the regions. Here we have an example of how we deployed and how we proceed during our missions. We essentially divide them in 3 different steps. We plan out the missions, which involves creating the routes which the LUVs are supposed to follow. This, of course, where we plan to send the vehicles to is highly dependent on the points of interest we find in that area. How do we find those points of interest? By taking a look at the data collected by the drones in the first step. So by fusing both, we can have a clearer picture of where should the LUVs be sent to. So we first start to plan out the mission, given that information. We deploy it, as we can see. And then we overview the mission while it executes. Although these vehicles are indeed autonomous, we still need to keep an eye on them. And not only them, but also, although this is a protected area, we have witnessed cases of vessels driving through this protected area and engaging in illegal activities. So we still need to keep an eye on them in case anything needs to be stopped or changed. So here is another picture or another video of the operation, again in the Praia dos Coelhos, in the marine park. And here we are able to see some information gathered by our LAUVs, mainly by the side scan sonar, as my colleague mentioned earlier. So given that plan we showed at the beginning, we were able to acquire these side scan images of the bottom of the sea in this particular region. We can, again, enforcing the fact that by using the drone as a first measure, we can pinpoint exactly what are our zones of interest. So here we see the Zoostera marina, or better yet, we could first see it through the image of the drone, and later on we planned the mission to pass through that exact location so that we could acquire or further investigate that part of the region. So by sending our LAUVs, we are able to generate the orthomosaic image of the area of interest and again further investigate that zone. This is an example of, this is not Praia dos Coelhos, this is another area in the park. So again, we are able to first acquire the picture and then move the LAUV to the point of interest. This is another example. This is another picture taken by our UAV, the DJI. Here we decided to take this picture as a request because there have been studies in the zone, in particular in Carvalho, where there was a project some time ago where a helicopter took pictures of the zone, again, to do a temporal analysis of the environment. And since that project stopped, we decided to assist them with having additional images of that same zone, again, to evaluate its development over the time. Up to this point, we have, as you can see, we have been since September 2024 been monitoring this area in particular. Again, both areas I have shown you before, in particular the Praia dos Coelhos. We have multiple. We have done a temporal analysis and spatial evaluation each time we go there, and further on into the project. So for the next couple of years, we intend to keep on going on the same missions and to the same areas to keep having a notion and gathering data so that we can actually improve and give our full contribute to the project that is DiverSea. Thank you very much.
Thank you very much, Lucrezia and Miguel, for those very interesting and visual presentation. We'll now open the floor for questions. Feel free to raise your hand and ask the question. If you'd like to briefly introduce yourself before your question, please feel free to do so as well. As a reminder, you can also type your questions into the chat at any time, and I'll, if you don't want to appear, and I can read them out. Anyone? No questions? Okay. I guess we got Xavier. Would you like to speak, or Lucrezia, Miguel, you have a question? I'll read it out for the recording. It goes as hello, I am Xavier Alonso from DTU. Thank you very much for the presentation. It was really interesting. I have a question regarding the cameras used for mosaicing with underwater vehicles. Why do you take still photos instead of recording a video and extracting frames for it? And also, what is the frame frequency you use? Is it fixed, for example, one picture every second, or does it depend on certain parameters, such as the percentage of features detected between consecutive images or the vehicle's velocity? I'm curious about how you manage to avoid leaving hidden areas between transects, while at the same time not taking too many pictures, which would require a lot of storage space. Okay.
Okay, so yeah, thank you for the question. So starting from the last one, so I'm curious about how you manage to avoid the living in the areas between transit while at the same time not taking too many pictures. So here the point is like if you are speaking about the transit, like the one that we should create through the optimal planning, this is we take in consideration the fact that the transit need to have a specific space in order to avoid specific area, and this is taken in account by the algorithm itself. While speaking about the traditional way of computing the mission, then the distance between the transect then are provided by information of first we check the bathymetry of the area that can change, but we try to stay in a specific area where we have a specific bathymetry in which based on the altitude in which we want to perform the mission, we can then select the distance between the transect and the frequency that as you notice, we didn't share any results. So what I was sharing in the previous part of the presentation was an example on how to operate. But then in the second part, we didn't share any underwater orthomosaics, but just the one acquired with the drone, because we are still in the process of changing camera in one of our AUV, because the one that we had before was not that much like we didn't have the performance that we wanted for our mosaics. So we are in the process of changing it. But speaking about the frequency that we use, the frequency was even in the first test in which we had the previous camera, the frequency was fixed and was the same. We didn't change the frequency during the mission. Okay,
Thank you.
thank you.
We have Nichols asking for the floor. Go ahead, Nichols.
Hi, hello. Can you hear me?
Yes, perfectly. And can you
Yes.
please present yourself if possible? Thanks.
Yes. Hi, thanks for the presentation. I am based in Trondheim in NTNU, so I'm in the chemistry department, and my involvement is a bit well, in different aspects, but partially is with the uh, sampling techniques as well in autonomous platforms. So here we are working with the USB, the Autonaut as well, and we try to implement also some uh, sampling for actual physical samples like the eDNA. So the main question was, the curiosity was about if in this prototype that Lucrezia you shows in the with the AUB. Is there any, it's passive sampler, so but there is no possibility of recording volume, right? And that's one, and the other one that in any of these cases or prototypes there is no means or way to apply to any preservative, I guess. So we're just curious about that.
I didn't understand very well the first question. So you're speaking about the prototype and the
It's for
Yeah.
eDNA.
Yeah, the prototype for eDNA, and if there is means to measure volume filter, or if there is means to apply some preservative to the sample. Uh, that was the main question.
So right now, I don't know if you want to answer this, Lucrezia, or I can. Right now, again, this is just a prototype. We are first evaluating if the samples we collect from that exercise you saw in Porto are indeed useful for those that want these samples. So we didn't go much further into how to preserve these samples. I can tell you that we are developing another version of the prototype, which focuses on gathering samples on different depths. So being able to open and close those cylinders you saw based on the depth of the vehicle. So that's going to be our next major improvement. But yes, when it comes to preserving the actual samples and measuring the volume, we are still in testing, and we haven't improved much on that part. Yes.
Yeah,
I would like
great.
to add
Also,
that
it's from the point of view qualitative yet so far than quantitative. Yes.
Indeed.
Yeah.
I
Okay.
wanted to add that actually the step of analyzing the filters after the mission is the NT new partners that is in helping in this. So we are waiting. So we did this experimental activity in Porto, and actually we were thinking of compute the volume of the water by simple math by based on the time and the actual mission that the vehicle did. So try to estimate the water that was flowing in the cylinders and then yeah, the part of the analysis is in continue to.
Yeah, I lost a bit that last part, but yeah. So I imagine it's Glenn who is analyzing the samples. I guess also probably you may not be on your domain, but the filters used in that test, do you know what type of filters were those? If
I
anyone
don't
can.
remember exactly the type, but was with us a guy from NTNU, Glenn. I don't know if you know
Yeah,
him,
yeah.
and yeah, I think he tried with two different kind of filters. I don't remember exactly the type. One was in a plastic case. And yeah, because during the mission we tested the eDNA sampling with the vehicles, and then in order to then understand if the data acquired by the prototype were something like the meaningful, Glenn in that case also sample the water with the traditional method, so with the pump and trying to use these filters. But the one that we're using inside the prototype, they were specifically cut around the shape, but I don't remember if probably he used both of the two that he used in the traditional method. So we have two kind of filters to compare in traditional methods and the prototype. But yeah, I don't remember the type.
Yeah, thanks a lot.
Yeah, eDNA and I mean the prototype which INEGI and Universidad do Porto LSTS is doing is really innovative. I think just eDNA is a world on its own, and I think we'll probably be having stuff on that and things coming out, and possibly even I mean there could be great discussions on the eDNA and how that's moving on. And NTNU obviously is also highly involved within this area. But thanks for that. Yeah, any more questions? So okay, I'll have a question. As you guys know, Lucrezia, Miguel, and some present, I'm also involved within work package of 5 of DiverSea citizen science. So I'd like to know if as it's becoming more important in biodiversity monitoring, do you see opportunities for marine robotics to connect with citizen science initiatives, or to make the data more accessible to the wider public? I'd like to have your thoughts on that.
I mean, if we talk about how technology is developing and how access to technologies such as this, which until years ago was almost impossible to picture, we can for sure say that with the help of citizens and in the future, I'm sure this type of vehicles, of course, in other types of scale, shorter scales, will probably become available to the public, such as it happened for example, for the Boston Dynamics robots. So I foresee a future where this type of technology will be available to the public, and with that, for sure, we will have more help from the citizens to actually require and acquire these samples. Of course, even nowadays, without the access to technology to everyone, enabling citizens to actually collect these samples is, of course, very useful and almost mandatory, even the amount of help we can have that way. But that's my point of view on it. I don't know, Lucrezia.
Yeah, I agree. We will have plenty of little robots swimming in our oceans and sea in a few months. So
I have another question if no one's asking a question. Policy-wise, if you had a policymakers in front of you, how would you sell marine robotics for the future? I mean, do you understand my question? If you had policymakers, how would you sell marine robotics and the importance for this type of biodiversity monitoring marine ecosystems?
I mean, one of the big selling points, I would say, is the fact that we are able to do such operations at much less, a much cheaper cost. For example, Lucrezia talked about how normal operations talk the advantages and the disadvantages of both types of operations. So the standard type of operation versus using autonomous vehicles to do so. And at least from our point of view and from the advantages and disadvantages we mentioned here, of course, we work with them. We are a bit biased towards them, but we also see how we can benefit from them and how they are better in multiple ways, such as cost, such as not putting, for example, lives of divers at risk, not polluting, during operations such as gathering data in the ocean. So those would be my selling points.
Any more questions? We can start wrapping up. Last chance. No more questions? No hands raised? Okay, so let's try to split the 1 hour webinar. So on behalf of the Mod Alliance team, I would like to thank you, both of the presenters, Lucrezia, Bernacchi, and Miguel, for sharing their expertise with us today. And thank you to all for joining and contributing to the discussion. We hope you found today's session insightful and it sparked ideas for further collaborations across the Mod Alliance community and beyond. So the recording of the session will be made available as soon as possible. Before we close, I'm pleased to announce the details of our next session. The 5th Mod Alliance webinar will be hosted by Marco Polo on Thursday, the 27th of November. Time to be confirmed. The speaker will be Natalia Gallo from NORC, and she will be presenting on the blue carbon mapping of European seagrass beds using remote sensing and oceanographic data products and the new Eurocarbon database. So please save the date, and we'll be sharing more details with you soon. With that, I'd like to thank you once again for joining us today. We look forward to seeing you at the next Mod Alliance webinar. Until then, take care and goodbye.
Thank you.
Thank you so much, everyone.
Take care, Lucrezia, Miguel.
Thank you for speakers. Bye-bye.
Yeah.